Good morning. The sun is back out again. Yay, we can go outside with our masks on now. How you guys doing? You ready for video number 5 for our solids and solubility chapter? We're going to have some fun with this one today. Started something with my kids. Anybody recognize that? You learn all your Vesper shapes from this game. Octahedron, tetrahedron. Oh, gotta work first. Then we'll have some fun. Things you do when you're trapped in your house with your kids. All right, anyway, we looked in the last video on predicting whether precipitate forms. Right? I got a solution here, got a solution here, stick them together, dilution occurs. Hey, do I form a precipitate or not? You don't always get one. Now you do in lab because we make it happen, but you got to realize the ion concentrations have to be high enough. So what we're going to do now in video 5 is just extend that one extra step. It's exactly like what we did. We're going to go through, predict whether precipitate forms, but if one does form, was that a complete precipitation? So this is used a little more in industry where you'll have a solution, maybe something found in a blood sample or a water sample you get from somewhere or a sample of seawater, and we want to extract from it as much of a particular ion as we possibly can. So commonly what we'll do is hold one of the concentrations. We'll form a precipitate by adding something to it. Hold one of the other ion concentrations relatively constant, maybe add it, as a buffer solution or something like that. And then start forming a precipitate by adding this other ion. And our goal is to pull out and extract as much of that particular ion as we can, typically a metal ion. So maybe it's a toxic metal ion. We want to extract that out of a water system or something. Whatever you need at the time. Maybe it's in your body, right? Got lots of lead in me from when I was a kid. We had leaded gas. Yeah. All right. So we're looking at precipitation completeness, just one extra step from what we did before. So after we mix two solutions, right, we're making the assumption that the ion product constant, or the reactant quotient QSP, is greater than KSP. If it is, shifting left, we get the solid, we get the precipitate. That will continue happening until QSP equals KSP, right? We'll keep precipitating out ions, pulling them out of solution. Q will start dry. So if K is here and Q is here, we're precipitating out ions. Q's dropping, Q's dropping, Q's dropping. And once Q equals K, we're at equilibrium. And now the ion concentrations are set and constant in solution. So we can actually look and say, well, this is what I had originally. This is how much is left in solution. How much did I pull out? Or we can say, how much do I have left? Right? So the qualification for whether a precipitation is complete is we pulled out 99.9. That's a pretty strict qualification there. We're yanking 99.9%, 99.9, 15.9994 oxygen. All right, 99, sorry. I have no filter with my brain in my mouth. 99.9% of those ions gets yanked out of solution, stuck, trapped into the solid that settles to the bottom of the container. Or another way to think about that is less than 0.1% of those ions are remaining in solution. I'd say we did a pretty good job extracting that ion out. All right, so it's a little slightly different than what we did before, where we're not going to take two solutions, mix them together, and have all of the concentrations get diluted. We're going to hold one of them constant using some chemical means and just watch one of them drop. And again, typically the metal, but not always. So, and that's why I said commonly done by holding one constant. That's usually going to be like a hydroxide ion concentration using a buffer solution or something like that. All right. So let's talk a little bit more about this, look at the steps for it, and then do a problem. That'll be it for this particular video. Oh, sweet. All right, so just to kind of reiterate some of the mumbling I was doing, I like to talk a lot, so sometimes I have to stop and write it down. Otherwise, you're like, what did he say? So my kids do all the time. What's Daddy saying? Slow down. As I mentioned, and I'm going to write it down, as long as QSP, the ion product constant or reaction quotient, is greater than KSP, where it's going to continue shifting to the left to form the solid. Remember, you got the solid on this side, on the reactant side, you got the ions on the product side. That's how you set up a KSP equilibrium. And if Q is bigger than K, it's going to shift left. The ion concentrations are too high. So it's going to continue raining ions out of solution into the solid. Q's dropping, Q's dropping, Q's dropping until Q equals K, right? At that point, we've achieved equilibrium, and now the cations and anion concentrations in that solution are constant now. You're constantly losing solid and dissolving it and reforming it back and forth, but the rates are constant, so the cation, anion molarities, or whatever concentration you use are set in solution. So we could calculate that using our KSP expression, right? So we could calculate the remaining ion, right? And we know, well, we should know the initial amount we started with. So we can actually calculate how much got put into the precipitate or how much is left in solution. It's pretty straightforward, right? So, and our parameters for completeness of precipitation is less than 0.1% remaining in solution, right? So the percent of the ion remaining in solution is just the concentration of the ion remaining in solution, which we calculate using our KSP expression, divided by the concentration of that ion originally in that water sample, blood sample, cerebrospinal fluid sample, spit sample, whatever sample you want, right? And then take that ratio and times it by 100. If that is less than 1%, right? That needs to be less than 1%. Less than 0.1%. My goodness. If that's less than 0.1%, that's a complete precipitation. All right, let's do a sample problem. All right, here's a kind of typical problem you're going to see. Let's say we have some seawater. Let's say we grab a 225 milliliter sample of that seawater. That's got various ions and whatnot, but let's say we're interested in the calcium ion. Whatever, could be any ion. Let's say in that seawater, calcium's 0.010 molar in that original seawater sample we got. And we want to extract that calcium out. So to extract it, we need to precipitate it out with something. Well, and we want to hold it relatively constant, so buffers are commonly acid-base, and OH minus would form a precipitate. If you look on your KSP table or look at a solubility chart, you find hydroxide solids are quite insoluble, or slightly soluble now, insoluble last semester. So very, very common. You'll see a hydroxide ion added via a buffer solution, maintaining a constant a relatively constant OH minus concentration to extract out alkaline earth metals, transition metals, because most of them will form precipitates with OH minus. Just snags them and pulls them out. So we're going to add a buffer to it. We're going to add 150 milliliters. Good to 3 sig figs. I got that little naked decimal there. Got to keep you on your toes. Of a buffer solution. So we're adding that. So we're adding a relatively constant OH minus concentration to precipitate out the calcium as calcium hydroxide. And that buffer solution, after we add it together, maintains the OH minus at a 0.37 molar concentration. Now, by adding these two, the calcium ion concentration is going to get diluted. It's going to drop. So we're going to have to do that dilution first, figure out what the calcium ion is, do our QSP versus the KSP and see if precipitation actually occurs, which if it didn't, this would be a stupid problem, right? So I'm guessing QSP is going to be greater than KSP. And we're going to precipitate out some of that calcium hydroxide. And then what we'll do is use the equilibrium expression to calculate how much calcium. Once QSP equals KSP, and we've achieved equilibrium, we'll calculate how much calcium is remaining in solution using the equilibrium expression. And then we just divide that by the initial amount after dilution, which will be a little lower than the 0.010 molar. Times it by 100% and see if that's less than 0.1%. If it is, we extracted or precipitated out completely the calcium. If it's greater than 0.1%, we failed at our job. Then we get fired and lose our car, lose our house, and terrible things happen. Start the problem for me. See what you can do. All right. First, let's figure out what the calcium ion is going to be after mixing. All right. So we've got dilution. Now, after mixing, let's draw a little line here. So after mixing and dilution, now you don't always have to do this calculation. Lots of homework problems and things like that. If the point, or like on a quiz or test, and it's time sensitive, and the point is not to test you on your ability to use the dilution equation, I may just say, hey, after mixing, these are the concentrations. Boom, and you're like, sweet, I don't have to do step one, and you can just jump right into it. And it's a relatively quick problem at that point. You just calculate QSP, compare to KSP, use the equilibrium expression, boom, 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 done, done, done. It takes you about 2 minutes to do. But the dilution, since we've got time here, we can go ahead and do that because that's more of a real life type of scenario, and mixing stuff and diluting them. All right, let's get the final volume, right? So V2, or V total, which will be V2, we'll be adding them together. So it's the 225 plus the 150. This is good to the ones place. That's good to the ones place. You're limited by the largest absolute uncertainty. So what's that going to be? Is that going to be, what do we got, 375? All right, so that's the final volume after mixing. So we're going to use the M1V1 equals M2V2 for the calcium, the 0.010 molar being M1, right? The 225 milliliters being V1 and the 375 being V2. And we'll calculate M2, and that'll be the calcium ion after we have the buffer solution. Now the OH minus is held constant, so we don't have to do that. Yeah! Here we go. Let's pop this baby out. So let's do the calcium ion concentration. That'll be our M2, which will be M1V1 over V2. And we've got those values right here. So M1 is our 0.010 molar. Our V1 is the 225 milliliters. And our V2 is our total volume, which is 375 milliliters. Those milliliters cancel out. Boom, boom, leaving us with molarity, right? You don't have to convert those to liters like we did in the last one. 2 significant digits in the concentration, 3 in the volume, so I'm limited to 2 sig figs. Okay, so I get 0.0060. So we don't have a non-rounded value, so it works out pretty nice. I get 0.0060 molar. So that will be our we're going to treat that as our initial calcium ion concentration after dilution, right? And then we're going to be pulling some out. All right, here we go. Let's do the OH minus, which stays constant. So the OH minus is 0.37 molar. And we're treating that as constant. Now that will drop a little bit, right? Just a little bit, like a buffer, but not enough to be measurable. All right, so let's take these, and if you want to work ahead, set up your equilibrium equation for the calcium hydroxide precipitate, set up your KSP, and your QSP. Let's see if a precipitate forms. So calculate QSP and look up your KSP value on your KSP table for me. Let's do it. All right, did you get your equilibrium equation? So we've got so what's our precipitate, right? We got calcium, which is +2, hydroxide, which is a -1. So that calcium requires 2 hydroxides to neutralize it out, to make it electrostatically neutral. So once we have that precipitate, it starts equilibrium. We're going to get a calcium ion. And look at the subscript of 2. We get 2 hydroxides. 2 hydroxide ions there. So that's our equilibrium equation. You always have to do that, right? Even if you don't know what the heck you're doing. Just write that down and, I hope I get a partial credit point. All right, let's calculate our QSP. I'm assuming a solid's going to form, because if it doesn't, we can't do the rest of the problem, right? So, but let's prove it. So QSP will be the concentration of the calcium ion initially after dilution times the concentration of the hydroxide ion after dilution, which is held constant by that buffer. We just calculated those in the first part. Let's plug those in. What was the calcium? 0.0060 or something like that? And again, we don't need to use units when we're doing Q and K calculations. The hydroxide, I think, was 0.37. And we got to square that. So we got 2 significant digits in both. So our answer is going to have 2 significant digits. So our QSP to 2, what did I get for 2 significant digits? 8.214. 8.2 vertical dash line 14 times 10 to the -4th. That's the QSP. We don't need to round that because I didn't really ask for that. Let's look up the KSP value. All right, so for calcium hydroxide, do I have it? Do I have it? There's so many forms. All right, I don't know what it is. Let's look it up. Let's look up C for calcium. Looks like it's right there. Do you see the calcium hydroxide? And if you don't know the formula, you can always see it there. Looks like 5.5 times 10 to -8. 5.5 times 10 minus 8. So KSP is 5.5 times 10 to the minus 8. So which one's bigger? Obviously, the Q is way bigger than the K. Right? So this is bigger than KSP. So that means the precipitate forms. We have a supersaturated solution, and it's supersaturated. The ion concentrations are too high, so it's going to get those out of solution to bring Q down. Remember, the driving force is to get Q equal to K. If Q is too big, you're going to lower those concentrations so Q drops, and we'll keep precipitating out that solid until Q equals K. And then that will stop shifting more to the left than to the right. And when Q equals K, now the rates are the same. But as long as Q is bigger than K, the rate going to the left is more than the rate going to the right. So the net effect is you're pulling ions out of solution. All right. So we know a precipitate forms. Awesome. So let's calculate, once we achieve equilibrium, once Q equals K, how much calcium is left in solution. All right. So let's calculate the concentration of the calcium remaining in solution. And once we have that, we can divide that by the initial amount after dilution, which was the 0.0060, and times that by 100. See if that's less than 0.1%. All right. So what is the calcium remaining in solution? Well, let's use our KSP expression right here, right? So if we use KSP is exactly the same as the QSP, so I'm being redundant here. We don't really need to write that because we have it right there. You just, Q is when you're not at equilibrium, K is at equilibrium. So can you see that the calcium ion remaining in solution will be the KSP value divided by that relatively constant hydroxide ion concentration from the buffer. So that will be KSP over the OH minus squared. That's why with these problems, they commonly hold one of those constant, right, to make this a little bit easier. Otherwise, it becomes a daunting problem. All right, we know KSP. We looked it up, so that's 5.5 times 10 to the minus 8th. We know OH minus, right? Relatively constant, 0.37. Don't forget to square it. All right. 2 sig figs, 2 sig figs. So I get 4.017. 4.017. Good to 2 sig figs. 4.017 times 10 to the minus 5th. And that'll be molar. So 4.017 times 10 to the minus 5th molar. Good to 2 sig figs. That's the concentration of the calcium ion in solution once Q equals K and we've achieved equilibrium. Now, it's not all gone, is it? And a lot of it's gone. But let's see what percent has actually been removed. All right, so the percent of the calcium, let's do remaining. So you could do, if you did the percent calcium removed, how much is in the solid, that would have to be greater than 99.9%. If you calculate the amount of calcium remaining in solution, that needs to be less than 0.1%. You can do it both ways. It doesn't really matter. This would be easier, I think. So we're just going to take that calcium ion, what's remaining in solution, divided by the initial. So let's take our 4.017 times 10 to the minus 5th molar. That's how much is in solution, right? Let's divide that by the initial amount. 0.006 molar. After dilution, and if there wasn't a dilution going on, a lot of times, again, they give you the concentrations after dilution to start with, so you can skip that first part that we did. All right, neighbors are doing their lawn. Hold on. Shut the windows. Woohoo! Sun's out. Weed whackers are out. 2 sig figs. Oh, that should be 0.006. Oh, I got it wrong. Oh, doesn't change the numerical value, but I need that trailing zero to give it 2 significant digits. Otherwise, I would have had 1 significant digit. That would change our rounded answer, wouldn't it? So always bring those significant zeros down, my friends. Otherwise, that happens. That 100's exact. So we're going to have 2 significant figures. I get 0.6695%. That'll round up. to 0.67%. So the amount of calcium ion remaining in solution is 0.67%. So sorry, that's greater than 0.1. Not good. That is greater than 0.1%. Not by much, but based on those standards, this was not a complete precipitation. We did not extract as much calcium as we wanted. And out in the real world, we'd probably adjust the buffer concentration to make sure that that happens. So I would say this is not complete, but pretty close, right? That's not a complete precipitation, but pretty close. Some situations might be good enough. Some situation, not good enough. There you go. That's how you calculate it. We're almost done with this chapter. Sweet.